is my great pleasure to stand here today and be able to introduce Paul Scotti for his PhD dissertation. So Paul's a PhD student in both my lab and Andy Lieber's labs. And before he came to OSU, Paul was an undergrad at GW, where he had already done some really interesting work on visual attention and object recognition. And then Paul came here to Ohio State to work jointly with both Andy and I. And it's really been a fabulous experience getting to work with Paul. Early on, one thing I remember is that Andy and I probably both spent a lot of time cautioning Paul about not spreading himself too thin and taking on too many different projects at once. And Paul would respectfully listen to what we were advising, and then he would go on and prove us very, very wrong. And so after about a year or so, I think Andy and I both just decided to stop worrying and let Paul do his thing. And Paul really has an uncanny capacity to take on lots of different projects simultaneously, and to collaborate with tons of people. So Paul, I believe, has in the past 5 years published papers with 6 different labs, both here at Ohio State and elsewhere. And as you'll see from his talk, his work is really outstanding. And Paul, as a scientist, is both creative and computationally savvy. But, in addition to Paul's research prowess and productivity, on a personal note, one other thing that I particularly admire about Paul is his commitment to science education and outreach. So among Paul's many accolades, Paul was awarded an NSF Graduate Research Fellowship. And as many of you know, the criteria for winning those prestigious awards are a combination of intellectual merit and broader impact. And Paul really passionately embodies both of those values. So I think even before he came to OSU as a grad student, I think even as an undergrad, he had started founding an organization called On Neuro, with the goal of more widely distributing research and making neuroscience research more broadly accessible. And so Paul was actually streaming talks online well before the pandemic and well before it became just the natural way of things. So Paul was very ahead of his time on that. He's also been involved in a number of other education and outreach activities. So one summer he went off for a few weeks to a program called Neuro Academy, and he came back having programmed this really cool interactive brain visualizer called EduCortex, which he made publicly available. It's really neat if you haven't checked it out. I encourage you all to check it out. And he's published this work not only in standard journals, but he's also published in journals like Frontiers for Young Minds, which is a journal aimed at explaining research concepts to children. And finally, one of the projects that he's not going to talk about today that he's been involved here at OSU is something called fMRI Playground, which he's been building an interactive fMRI analysis tutorial geared towards people getting an introduction to fMRI research. So it's really been fabulous to have the opportunity to work with Paul over these past 4.5 years. Paul already has a postdoc lined up at Princeton in Ken Norman's computational memory lab. So he'll be headed there in April or May. And, we really look forward to seeing what Paul continues to produce and all the neat work that Paul does at Princeton and beyond. And we really will miss him deeply here at Ohio State, but we are very proud to watch him go on. And so on that note, I will let Paul tell you about some of the really cool work that he's been doing over the past several years here as part of his dissertation. And I hope you all enjoy hearing about Paul's work as much as Andy and I have really enjoyed working with Paul over these past few years. So here's Paul Scotti.
Thank you so much. Today I'll be talking about 3 projects that I completed during my PhD here at Ohio State. These projects can be roughly subdivided into 2 topics. The first being, how can our visual memories be distorted? I'll be presenting 2 behavioral projects spanning working memory distortions and long-term memory distortions. The other topic is how to reconstruct content from the brain using neuroimaging methods. So, for instance, how can we use brain activations from someone lying in a scanner in order to predict the contents of visual perception and visual memory? So first, let's talk about memory distortions. And what do I mean by memory distortion? I think that we can draw an analogy to optical illusions, which would be a perceptual distortion. Here's one example called the tilt illusion. How this illusion works is that you should be perceiving the outer grating and the inner grating as both rotating slightly back and forth. However, in actuality, only the outer grating is truly rotating. The inner grating is completely stationary. And so this is a perceptual distortion because your perception is that both gratings are rotating, but in actuality, the visual input is such that the inner grating is not rotating. And you can verify that this is indeed an illusion by doing something like overlaying red lines on top of the image. And so the question here is, how can we translate these kind of perceptual distortions into the memory domain? Because how can you observe a distortion occurring internally in your mind, right? It's not like you can overlay red lines on top of an internal memory representation. So how do you explore this kind of thing in the research setting? Well, the most common way that memory researchers explore memory happens to be incompatible with the investigations for memory distortions. The most common way that memory researchers explore how memory works is to use something called a recognition test. Basically, you have participants memorize a lot of images, and then after they've studied all of those images, you test them one at a time, asking if they recognize an image or not. And so this is not really compatible with memory distortions because you don't get any measurement to the quality of the memories that are being reported in a test such as this. All you get is correct or incorrect for every image. So you need to use a different kind of task and method for analyzing data if you want to explore memory distortions, which is what we'll be talking about here. Let's use an example to introduce what I mean. Let's say that you're walking your dog and you look out across the street and you see the following occur in front of you. So you've just been witness to a car chase, and Officer Golomb is here to investigate. She comes to you and asks, what was the color of this car that just came in front of you during that car chase? And please report using this color wheel. And Officer Golomb is quite smart here because she knows the value of a continuous report task. And that's because a continuous report allows you to more finely investigate different types of memory. Let's talk about different types of memory reports that might be observed. Let's say that Officer Golomb interviews 100 onlookers who had been witness to the car chase, asking every one of them what was the color of the target car. If the 100 people who were interviewed had just randomly been clicking on the color wheel, then that distribution of color reports that he obtains would look something like this. And you would be accurate to deduce that basically nobody remembered anything about the target car if their distribution of responses across all the people looked something like this. On the other hand, maybe people did remember the color, in which case they would report an orange on the color wheel. However, more accurately, people are not perfect. So if you were to visualize this kind of memory report, it would look something like this. A normal distribution centered on the correct color. So now let's talk about how memory error is not confined to just guessing. One possible outcome could be that people remember or report the color of the non-target car. So if that were to happen, you would visualize that distribution as something like this, a normal distribution centered on the incorrect non-target car's color. And this would happen if there was something like a misbinding that occurred in memory between the identities of the vehicles and the colors of those vehicles. Another kind of memory error could be a shift error, which could be further subdivided into repulsion bias and attraction bias. Basically, this would occur if people roughly remember the color of the target, but it's been systematically biased either away from the non-target color, repulsion, or biased towards the non-target color, attraction. And so this might occur if there is some sort of interaction between these two mental representations of the two cars. You could kind of think of it as like how in the tilt illusion, the outer grating was changing your perception of the inner grating, biasing it to rotate back and forth. Likewise, in this case, maybe the two memories of these cars are interacting such that the memory for the color of the target has been biased relative to the color of the non-target. And so the goal here, given that we've been able to divide these memory reports into different classes, is did swapping actually occur? Did repulsion or attraction actually occur? We would like to be able to quantify the proportion of responses from the 100 people into the relative proportions of how often these kinds of reports were observed. So in other words, what percentage of those 100 people were guessing? What percentage was swapping? If there was repulsion or attraction, how large of an effect was that? And the way that you can get numerical estimates for this is to use a computational model called the probabilistic mixture model. So we'll be using this probabilistic mixture model in our first experiment here, which was specifically focused on investigating repulsion bias in working memory. So let's talk about repulsion bias a bit more. Repulsion bias has previously been observed to occur in a working memory task when the items being remembered are somewhat similar looking and when they need to be maintained in fine detail. So for instance, a task like this might lead to repulsion bias, where a person needs to remember a red and a purple square over the course of a blank delay. And then in this case, the right square gets queued, so the participant would need to click the color that they think was the right square's color. And when they do so, experimenters have observed that there's a systematic tendency to report a slightly bluish color rather than true purple. In other words, people are systematically biased in a task like this to report the color repulsed away in color space from the non-target color. The question remains, what caused this kind of repulsion bias that's observed behaviorally? Could the mechanism that leads to this kind of repulsion be explained due to a perceptual mechanism rather than a purely memory mechanism? One possibility is that the same mechanism that causes the tilt illusion is causing the repulsion bias observed here. And you could imagine that this could be the case because there's been previous work that shows that optical illusions can continue even after the cause of that illusion is removed. So in the tilt illusion, for instance here, the inner grating will appear repulsed in orientation from the orientation of the outer grating. But even after you remove that outer grating, so that only the inner grating is now visible, that inner grating will still appear to be biased or repulsed for upwards of half a second or so. In other words, this is a sort of after image of the optical illusion. And this after effect could similarly be used as the reason for why you find repulsion bias in the color task above. Basically, immediately after you encode the red and purple square, there's a bluish after image for the right square that eventually leads to the behavioral repulsion bias. And that could be therefore explained without any mechanism of the red and purple squares actually interacting with each other as mental memory representations. Rather, it could just be explained as a sort of after image perceptual effect. So that's what we wanted to explore here. Can memory representations truly interact in working memory? repelling against each other. So we used the following task to explore that. On every trial, there were two real-world objects that were displayed side by side, and they were both colored, such that they were somewhat of a similar color. And you can see in this example, memorizing an orange vase on the left and a green globe on the right. They have 1 second to encode that information to working memory. And then both the images are masked by randomly colored pixels, followed by a blank delay of either 800 or 2800 milliseconds. Then one of those two objects is presented again in grayscale in the center of the screen, and the participant needs to click the color that they think was the original color for that object. Then they report their confidence, basically the smallest range of colors that they think contain the original color, and then they get feedback and monetary bonus based on performance. Here's a demo of what that looks like. Okay, and now let's look at what the results are across 81 participants. We have two conditions here. Half the trials were of a short blank delay and half the trials were a longer blank delay. And so what I'm visualizing here are the error distributions for those two conditions. You can interpret this as this histogram where 0 degrees reflects the perfect color report. 180 degrees reflects reporting the color at the opposite end of the color wheel to which should have been reported. And I've aligned the responses such that if they were reporting a color that was towards the color of the non-cued object's color, the non-target object's color, then that error would be positive. So basically, if they were reporting the non-target color, that would occur at 45 or 90 degrees here on the x-axis. And so visually, you can see a bit of a bump in both of the conditions where people were reporting the non-target color rather than the actual target object's color. And so you can imagine that there was at least some sort of swapping going on. But we want to be a bit more precise when interpreting the existence of memory errors here, and that's why we turn to mixture modeling. With a mixture model, we can get actual parameters for how often swapping, repulsion, and so on occurred. For instance, here, target 0.811 means that 81% of all of the reports for the long delay were attributed to the target distribution. And about 9% of all of the reports were random guessing. And so what we were specifically interested in here is the shift parameter, where a negative value would reflect repulsion. What I didn't mention before is that this mixture modeling approach is Bayesian, and that basically means that instead of getting a single number per parameter, you get a distribution per parameter. And so I'll be plotting here the posterior distribution for the shift parameter in each condition. The individual dots here refer to individual participants, and the error bars at the bottom you can interpret as there is a 95% probability that the true parameter value is within those error bars. And basically the takeaway here is that most of these participants were showing repulsion, and the repulsion was greater for the long delay compared to the short delay, meaning that repulsion bias here was indeed observed without any perceptual alternative explanation. So we are observing here true mnemonic repulsion bias. And I can say that because, first of all, the encoding and the retrieval demands for both of these two conditions were identical, and yet we found this difference in repulsion magnitude across the two conditions. And also, we specifically made it so that the target object that gets represented in grayscale is presented in a different spatial location compared to when it was initially studied. And this means that the after image explanation of the purple leaving a bluish after image in that same spatial location wouldn't really work, because now the after image would not be in the exact same spatial location that would allow for that same mechanism, perceptual mechanism, to work. Given that we've now isolated experiment one's repulsion bias to the maintenance period, in other words, the repulsion occurred during that blink delay, we further wanted to explore the mechanism for repulsion bias during that blink delay. We had two ideas, an active and a passive account. The passive account suggests that the reason we found more repulsion bias in the long delay is because if you need to maintain colors across a longer time period, then those memories are probably going to be of worse quality. And if you have a worse quality memory, it might be more prone to distortions like repulsion bias. The active account, meanwhile, suggests that it's not really the quality of the memories that's driving repulsion bias. Rather, it's the fact that you're having to actively attend to the two items during that blink delay. And so you're really trying your best to make sure that you don't confuse the two items in your mind during that time period. And that active attention to keep those memories distinct causes a repulsion bias effect, pulling apart the representations. And so to figure out which of these two accounts is true, we designed this experiment, which is the same as the last one, except we replaced the short delay condition with a filler task condition, where participants were shown two objects above and below the fixation cross in the center, and they had to click using their mouse the object of the larger real-world size before the 2 seconds were up. So in this case, they'd have to click the car within the 2 seconds that these two images were presented. And basically, this is serving as a distracting task. And the passive account would posit that a distracting task during that delay period should further make the memory representations for the colored objects worse, meaning that repulsion bias should be increased. The active account, meanwhile, suggests that a distracting task makes it harder to actively attend to the colored items, and therefore repulsion should decrease, or maybe there won't be any repulsion at all. And we observed exactly that. The filler task led to no behavioral repulsion, and the active account was supported. Meanwhile, we replicated the repulsion bias that we observed from experiment one in the blink delay condition. And this leads to a somewhat counterintuitive result. For better maintained memory items, we observed more repulsion bias. Usually you might think of if your memories are of a worse quality, then they're going to be more prone to memory distortions. But in this case, we didn't find that. We found more repulsion for better memory quality. So in summary for this project, what happens when working memory items are maintained in fine detail? Repulsion bias. And specifically, this repulsion bias is due to active interaction of the memories. I'll also note that this was the first demonstration of working memory repulsion bias without using spatial or temporal cues and using real-world objects. So previous studies looking at this kind of distortion stuff have used very simple stimuli like colored shapes or the orientation of a line. And you might reason that they find these kind of effects because the images that are being memorized are already so similar looking to each other and confusable. So it's really important that in our experiment, we use real world objects so that our findings are more generalizable to the real world. So you can find this, we found this kind of repulsion bias for objects such as a green sofa versus a yellow tennis ball. And so the identities of the objects being memorized don't need to be the same to observe these kind of distortions. So let's move on to long-term memory. And specifically, I'll first point out differences between these memory systems. Working memory refers to active manipulation and holding of information and is capacity limited. For instance, you cannot memorize a 100-digit phone number in working memory. Long-term memory is for passive storage of information and it doesn't really have a capacity limitation. There's no cap to the number of memories and the quality of those memories that you can form throughout your human lifespan. And so given that the long-term memory system has less constraints relative to working memory, it might stand to reason that it's not going to have the same sort of distortions. And so that's what we investigated here. Is long-term memory also similar to working memory in the kinds of distortions that can emerge? One of the reasons why I think long-term memory hasn't really been investigated to the same degree as working memory in terms of stuff like repulsion and attraction bias is that it's a lot harder to figure out what the reference point can be for which repulsion and attraction can then be observed. In working memory, it's pretty simple. You have two items that you memorize, and then the one that you're not tested on is the distractor or the reference point for which you can then measure relative repulsion and attraction. But for long-term memory, how those kind of experiments work is that you have a study phase where you memorize many, many, many images, and then you get tested on all of those images at once later on. And so you can't have the same sort of reference point for every single item that got memorized. Instead, you would need a more general reference point. And so we turn to the statistical regularities literature. Statistical regularities refer to repeated patterns in the environment, and we know that long-term memory cares a lot about statistical regularities. For instance, infants learn what is a word and what is not a word based on regularities of speech sounds. The co-occurrences of phonemes, the frequencies by which different sounds occur together, that's how infants learn language initially. And in adults, visual attention has repeatedly been shown to be implicitly biased by regularities in our spatial environment. And so our idea here was to induce distortions in long-term memory using color regularities. So more specifically, we used this kind of design where participants studied many different colored objects and they were tested on them all at the end. However, we did not tell people that we were manipulating the color sampling of the studied objects. Namely, for every participant, they had a randomly selected rich color, and that rich color would be used as the color of 30% of all of their studied objects. Meanwhile, the remaining 70% of studied objects were randomly colored across the other colors in the color wheel. And so we wanted to see whether the memory reports for the non-rich objects would be distorted relative to the rich color. So here are the error histograms across 175 participants. And I've subdivided the histograms based on the relative distance and color space between the tested object's original color and the rich color for that subject. So in other words, looking at the short plot here, this is only visualizing the reports given for objects that were originally sampled in color space 23 to 67 degrees away from the color of the rich point. And so I've aligned all of the reports such that the red dot here on the x-axis is that rich color. And you can see that there's a bit of a bump here where participants were indeed reporting the rich color, even though the original object's color was not rich. And that persisted across objects that were colored farther away in color space compared to the rich color. So for instance, you can see the bump here and the bump here. So people were indeed distorted, at least to the extent of reporting the rich color rather than the actual color of the object a good portion of the time. We use mixture modeling to look at repulsion and attraction bias. And as you can see, the direction of that bias depended on the relative distance in color space. So we found repulsion when the objects were originally colored similarly to the rich color, and we found attraction when the objects were originally colored dissimilarly to the rich color. In other words, similar representations repelled, perhaps due to the higher confusability between similar memories. And more dissimilar memories are not as easily confused, and perhaps that's the reason why instead of repulsion, we observed attraction. And it's important to note that this kind of observation has been previously observed in working memory. In other words, these results were very consistent with what you would come to expect from working memory studies, meaning that long-term memory items are indeed subject to the same kinds of distortion as the working memory system, despite the fact that the long-term memory system doesn't have the same sort of constraints as working memory. We found swapping and shifting that was consistent with what you would expect from working memory studies. This was also the first demonstration of statistical regularities acting as a reference point to induce memory distortions. It's also, to my knowledge, the first long-term memory experiment to show simultaneous swapping, repulsion, and attraction. And also the first long-term memory experiment showing repulsion bias using a continuous feature space, such as color here. So let's take a step back and think about some of the limitations that come with a task and method like this. Two obvious ones are these. First of all, you're limited to the continuous feature space. So we use color. Other people have used things like spatial location and orientation of a line and shape. And these are all things that can be manipulated and reported along a continuous dimension. However, using something like realistic photographs, you don't have a single continuous dimension for which people can report their memory quality on. And therefore, truly naturalistic real-world images like photographs are not compatible with this kind of task. However, I would argue that the advantages of being able to characterize the relative proportions of different memory distortions is very valuable and is beneficial to the degree where you lose some of the realisticness of using real images. But in return, you get better ability to explore memory errors and the mechanisms of memory. Another limitation is that you need hundreds of trials per subject for model fitting. And this is because you are approximating distributions. So you cannot use this technique given only a few trials. You cannot get individual trial estimates for memory distortions. And finally, one more limitation, which is perhaps more insidious and might be raised by a reviewer, is how can you truly isolate memory processing from motor and decision-making processing? So for instance, there's the motor process of physically moving your mouse to click the color on the color wheel. There's also the decision-making process of determining what color you're going to click on. And those are technically separate from the internal memory process by which we want to explore. And so in order to truly take away those motor and decision-making processes, you would need an experiment that doesn't have behavior as an output. And so how can you observe memory distortions without the participant giving you any behavior? Well, the answer to that is to use neuroimaging. And so in this project, we will be looking at how neuroimaging can decode stuff like memory representations from a methodological perspective. So for instance, to repeat myself, we want to be able to do something like to predict what was the color of this bell that the participant is thinking of based purely on a model that gets brain activations as the input. Now, the traditional way to accomplish something like this, to decode mental representations, is to use something like a linear classifier. However, linear classifiers are a bit limited in the sense that they are not based on neurophysiology, and you cannot predict untrained classes. What I mean by that is if you train the model on red and blue, the model can only predict red and blue. It'll never be able to predict green. And so if you want a model that can predict, for instance, in our case, any color on a color wheel, that would be 360 colors. You'd have to train the model on every single one of those colors. And that's not very efficient. So a way that would work to accomplish this task is a more nuanced approach to decoding, Specifically, I'm talking about encoding and decoding models, which are a bit more flexible to this kind of approach. And they've been used to do things like reconstruct orientation, human faces, musical timbre, verbal words. And in this project, we will specifically be focusing on one kind of encoding and decoding model called the inverted encoding model. And specifically in this project, we have introduced some improvements on the inverted encoding model. So I'll first be talking about the standard implementation of IEMs. Then I will be talking about how we improved this method. I'll then validate our improved or enhanced IEM procedure on real data, and then finally link it back to the behavioral modeling from before. So with inverted encoding models, the goal is to predict inputs given brain activations. And we can divide this into two main steps. First, build an encoding model, which basically accomplishes the opposite of what you want. This is a model that transforms stimuli into brain activity. Then step two is to invert that model into a decoding model, which does do what we want it to do, which is predict stimuli given brain activity. So I will demonstrate how this works using a toy example. So in this example experiment, we have a fake person looking at different colored squares on each of 8 different trials. So we have these 8 different colored squares that are looked at individually one at a time. And for each of these trials, we also have measured brain activation from 6 voxels. A voxel is basically a 3D pixel in the brain. It encapsulates a large population of neurons. And so we get these trial by trial level brain activations for every voxel. And the goal is to train the encoding model on the first 4 trials. Then we can try to predict or decode what colors were presented on the held out last 4 trials using the brain activations from those trials. So to build our encoding model, we're first going to rely on some principles of neurophysiology, namely neural tuning. And this is the idea that there will be a subset of neurons that are receptive specifically to certain colors. For instance, maybe there's some neurons that are receptive to red, and then they'll be moderately receptive to purple, and then baseline receptive to every other color. And so the idea here is to create this model which is composed of a series of these kind of tuning functions tiled across the feature space of interest, where in this case, our feature space of interest is color, but this can be applied to any sort of continuous feature space. So now that we have this basis set of neural tuning functions, we will then be creating a so-called matrix of channel responses. So how does this work? Basically, every trial, we take that color, plot it on the x-axis here, and see where it intersects with each of the 9 tuning functions here. We record values for each of those tuning functions, and we save those values in a matrix like this. And we do that for each of the 4 training trials. So this is the matrix of channel responses. We take that matrix and we will multiply it by an unknown weights matrix to get our observed brain activations for those first 4 trials. We can estimate the values for the weights matrix here using linear regression, like so. And this completes the trained encoding model. Now we want to get our decoding model. To do that, we will invert this encoding model. To do that, we keep our weights matrix the same, and now we are trying to estimate the channel responses given the observed brain activations from the held out test trials. Again, using linear regression, you can estimate the values for this. And then importantly, you can replot these channel responses back into tuning functions. Before in the encoder, we took the tuning functions and then got the matrix of channel responses. Now we're estimating the channel responses and replotting into tuning functions. So for trial 5, we have a reconstructed neural tuning of this, where it's maximally receptive to what appears to be a green color. And indeed, trial 5 was green. We can plot the tuning functions for all 4 of these test trials like this. And then according to the standard implementation of inverted encoding models, you would align them all to the point that represents 0 error. And so ideally, what you'll find here is a Gaussian distribution, in other words, the shape of the tuning function, aligned at the dotted line here. So there should be the highest amplitude at the dotted line. Then you can average across all of these trial reconstructions and evaluate that average using a number of possible metrics, but in this case, I'm showing amplitude. Basically, you take the value of the reconstruction at the dotted line, and you see if that value is higher than what would be expected by chance. And if it is, then you conclude that your model works, and you can decode stimulus-specific information in that brain region. So now let's talk about some of the ways we improved upon this model. The first modification that we introduce is iterative shifting. Now, this is not a novel modification, but it is an important one as setup for the more novel modifications. And how iterative shifting works is you get reconstructions that look like the bottom right rather than the bottom left. The bottom left reconstructions are limited in that they only have 9 data points, and that's because we use 9 tuning functions in the basis set. But ideally, we want reconstructions that look like this, where we have a data point for every single color. And you can do this very simply by just repeating the entire IEM procedure with slightly shifted basis channels for the basis set. So for instance, combining basis set A with B gives you a reconstruction that's composed of 18 points. Our second modification, which is more novel, is to suggest that you really shouldn't be aligning and averaging reconstructions. Instead, we propose that for every reconstruction, you correlate it with a basis channel centered at every single possible color. And then wherever you find the highest correlation between the basis channel and the reconstruction, that determines the predicted stimulus for that trial. So for trial 5, the highest correlation between the dotted line and the reconstruction occurred around here, and that is green, and so the predicted color for trial 5 is green. You can do that for all of the trials, and then so to see how well your model did, we advise something like just taking the difference between the predicted stimuli versus the actual stimuli. So for instance, mean absolute error here, meaning that on average, you are 36 degrees of error in predicting the color of that trial. And so the advantages of these modifications are that you get meaningful units, you get, as compared to arbitrary units with something like amplitude. You get trial by trial stimulus predictions, you get an actual stimulus that's predicted for every single trial, and you get these goodness of fit values for every trial. The R values here are the goodness of fits. And so you can interpret these R values as basically how confident you can be in your predictions. And this is a non-circular procedure because you're simply correlating the dotted line, the best fitting basis channel, with the reconstruction. You're not using the actual stimulus in the calculation of the R values. And so you can do really interesting things with these goodness of fit values. For instance, you can exclude trials that are particularly noisy from your data set and therefore increase the statistical power of the method. So for instance, we have used simulated data sets across many different parameters and conditions. I'm just plotting one here, where we show that if you exclude the worst fitting, the noisiest trial reconstructions, your neural reconstructions improve. And that's reflected by the mean absolute error getting better and better with increasing trial thresholds. Likewise, we validate our EIEM method on real data sets. Here are 3 real data sets spanning perception, attention, and memory. And I'm only plotting one subject for each of these, but we've validated across all the subjects in multiple conditions. But basically, we show that you can use EIEM to do things such as decoding the horizontal spatial position of a spherical stimulus, decoding the attended orientation of a grading, decoding the working memory orientation held in mind during a blank delay, And so we truly show that these modifications improve the standard implementation of inverted encoding models because they are able to do things. EIEM is able to do things such as evaluations in meaningful units, trial by trial predictions. I wasn't able to talk about this here, but it's more robust to methodological concerns. You're able to do things like trial thresholding with goodness of fits, given that you set an a priori cutoff of I'm going to exclude, say, the 20% noisiest trials that we get. We validate across real and simulated data. And also I have a publicly available open source Python package, which allows researchers to implement our improved method in one line of code. So now let's link back together this neural model with the behavioral mixture model. They are different in the sense that one specifically models behavior, one specifically models neural data. However, they are complementary because they are both limited in the exact same way. They are both limited to continuous feature spaces. And therefore, they're very complementary because you can investigate neural and behavioral distortions within the exact same experiment using the same kinds of stimuli. And so there's a lot of potential here for future investigations of things like memory distortions. As one example, in the attention data set here, we showed that there was a strong positive correlation between the neural error, the neural predictions versus the actual presented stimuli, and the behavioral error, the reporting on the continuous report task. So this shows that they can be linked together in the sense that when people were worse behaviorally, we were also worse at neural decoding. Likewise, we could isolate behavioral swapping in trials of this experiment, and we found that the neural reconstructions for trials identified as swapping likewise had these reconstructions centered at the wrong stimulus, the swapped location. So the swapping of observation behaviorally translated to swapping neurally. So let's tie everything together. How can our visual memories be distorted? Well, you can investigate memory distortions using a continuous report task analyzed using mixture modeling. And that way you can get quantification for things like swapping, repulsion bias, and attraction bias. You can think of memory distortions as similar to a mental optical illusion, but we show that the mechanism for these are separate. And we also show that the memory distortions observed in working and long-term memory can be generalized to the same framework. Finally, regarding neuroimaging, we demonstrate the enhanced inverted encoding model as a way to reconstruct neural content for internally held representations. And this is a very promising future for neuroimaging investigations of memory distortions because of how complementary mixture modeling is with inverted encoding models and how they're both limited in the same way. So I'd like to thank you for listening. I'd like to thank my advisors, Andy and Julie, co-authors Yulim and Jiagong. I'd like to thank my parents. I'd like to thank all the members of the Golomb and Lieber labs and everyone that's supported me throughout these years of grad school. Thank you so much.